Greetings of the day to all of you. Today we are going to learn about matrix.
We will watch 2 videos about matrix converters.
I believe I already introduced this converter
So you can check the
last
lecture.
semester in our course on applied power electronics. However, this lecture is going to be a little more detailed as compared to the previous lecture. So basically, what are matrix converters? They belong to the class of AC to AC converters.
AC to
So we have
AC
direct
converters.
conversion from
Direct
three-phase
conversion
AC or
from
polyphase
AC to AC.
Again polyphase AC at variable voltage.
So input is AC, output
The
is
advantage is
AC.
offered by
We
matrix
can change
converters as compared
voltage
to
and
classical
frequency
cyclic
as
converters,
an
which are
output.
also AC to AC converters, but they use thyristors. Is that matrix converters offer unrestricted frequency conversion, which means you can attain any frequency.
So you can obtain any frequency
of the
at
source.
the
You
output.
can attain any frequency at the load side, irrespective of the frequency of the source side. Now, the circuit shown over here is a circuit of a 3-phase to 3-phase matrix converter. You have a 3-phase AC supply available with a
So
fixed
this is
frequency
3-phase AC supply, 60
and at the
hertz,
output, which is a
220.
small alpha
This is
AC,
output.
you can attain
The
a
voltage and
three-phase
the
voltage
frequency can be
at
adjusted.
of any magnitude less than the
any
magnitude of
magnitude.
the input and at any frequency.
And any
The
frequency.
condition is that the maximum voltage available at the output of the converter is only 86.6%.
So the maximum is
input
86,
So the voltage transfer ratio
86.6%.
limited to 0.866. Anything between 0 to 0.866 times the input can be made available at the output. Now, the basic idea behind a matrix converter is that you have 3 groups of switches, and each group
So we
has
have 9 switches,
devices.
3 by
So
3.
we have switches SAA in the first group, which basically samples the input phase capital A and the output phase A.
So A
This
is
switch
input, capital A input,
samples
small a
the
output.
input phase B at the output phase A, and the third switch SC
So this means
samples
input,
the input
this means
phase C
output.
at the output phase A. Similarly, A, B, C of the input can also be sampled at the output phase B through switches A, SAB, SBB, SCB. Right? And finally, the 3 input phases can also be sampled at the output phase C, again through 3 switches SAC, SBC, and SCC.
So totally we
you
have 9 AC
9
switches.
devices in a matrix converter. Now, this was about the basic principle of a matrix
So this is the basic principle of matrix converter.
brought at any output phase by means of this array of switches or a matrix of switches, as you may call it. Let's talk about the switching states of this
So now
converter.
we discuss
Now,
switching
we know
states.
that there are 9 switches, and we
9
also know that
switches.
each switch can be on or off. So either
1 or 0.
let's talk about
Okay.
SAA. It can have 2 possible switching configurations. It
So
is
two
either
possible.
on or it can be off.
1 or 0.
Similarly, SBA will have 2 switching configurations. SCA will have 2 switching configurations, so on and so forth. So a total of 2 raised to the power 9. This will happen 9 times.
So each
So a
switch
total
has
of
2
power
possibilities,
9
but we have 9
which is
switches.
500.
So how many states can we have?
in this converter?
512.
Because the converter has
So totally
partial
512.
Therefore,
It is
theoretically,
too
it
many.
is possible that 512
So can you
switching states
select one of them?
exist.
It is impossible.
However, all of these 500 switching states are not feasible.
So not feasible. Not every state is
There are
feasible.
certain switching rules that the matrix
So
converter
there are
has
some
to
rules.
follow. The first switching rule is that the converter cannot be given those switching states that can cause the input.
So input cannot be short
For
circuit.
instance,
So input cannot be short
the
circuit.
first rule is that the input phases should not be short.
Short circuit. So input phase cannot be short circuit. because it
For
is
instance, I switch on
AC
SAE
source.
as well as SBA, which means that the two phase voltages VAA and VA and VB input phase voltages have been shorted
So
by
if
means
you
of these two
turn on
devices.
this one,
So that's like
AB
a
short
short circuit
circuit.
condition. It will cause a lot of current to flow through the converter and the devices will get damaged, of
Then
course.
the device will
So this condition has
damage.
to be avoided, which means that in any group at a time only one device has to conduct.
Only one switch
So only
can turn on.
SAA or
If more than
SBA
one,
or
then short
SAA has to
circuit.
conduct, which means that only one device will conduct in each group. Similarly for group
So
B
only
and
one here, only one here, only
The
one here.
second rule is that at least
So the second
every
rule
output
is
phase,
the output side.
input phase voltages, but every output phase, assuming that we have an inductive load
This is
at
output.
we cannot interrupt current through
We
an
cannot
output phase.
open
So
all
output
of
phase
the
should
switch,
always be
otherwise the current cannot flow. So at least one switch should be
some
turned
input
on.
phase. In other words, you can say that output phase should not be open.
Open. So output cannot be open. Input cannot be short circuit.
That each output phase should definitely be connected to one.
At
of
least
these.
one.
It should be connected to
And,
only one, but it
not
should
more than
definitely
one.
be connected to one output phase. Otherwise, it will be opened. There
So
will be an
if
open
this
circuit
open,
condition.
you
If
cannot
one
provide
of these only.
current
Which
shift.
means that a condition like 0, 0, 0 is not feasible.
if
because
0, 0, 0, then how can you create 5 ampere at
but
the
it will
output
definitely
side?
open circuit the load, and that is not desired because the load is inductive and sudden open circuiting of
So you
inductive loads
open
is
the inductor,
inadvisable.
then
So
you create a
keeping
spike.
these two switching rules in mind, we
So
know
this is
that
basic
every
rule.
group
Input
only
cannot
one
be
switch
short
should
circuit.
conduct,
Output
at least
cannot
one
be
switch
open
should
circuit.
conduct, right? Which brings us to the total number of feasible switching states.
So how
in
many
matrix converter.
feasible switching states?
So only one device should conduct, either SAA
So
or
only if and
SBA
only
or
one
SBA.
switch
So
can
you
turn
have
on.
a total
In
of
this
3
group,
switching states possible for this group, a total of 3 switching states possible for the other group,
This
and
three,
a total of
this
3
three.
switching states possible for the third group, which makes
So how many switches
possibility
do
of
you have?
27 switching
27.
states.
So
A
only
total of
27.
27 switching states are
Because
feasible in a
if
matrix
and only
converter,
one
practically
switch
feasible
can be
in a
turned
matrix
on in
converter.
this group,
If you compare this with
If
a
and-
voltage source inverter,
then if only
then
one
you
switch
had,
can turn on this
in
one,
each leg
if
you
and
had to
only
make
one
one
switch can
device
turn on
conduct.
this one.
You had to choose one between 2 devices. In case of a matrix converter, you have to choose one between 3 devices every time.
So
right?
one
Therefore,
between
just
3
like in
devices.
VSI, one device was a node of the other. Here, that is not the case because you have to choose one between 3 devices, right? So, because when you are choosing one device between 2, it automatically means that the other device is a node of the first device. However, here you have to choose one between 3. Therefore, a direct NOT relationship does not exist in a matrix converter, which also makes the modulation or the control of matrix converters slightly more complicated because every time
So
you have to
we totally
make
have
a choice
27
of choosing a device
choice.
between 3 devices. Also, there are a large number of switching states, which gives you, of course, certain advantages, which we will discuss later, but it also makes the modulation or control slightly difficult.
Difficulty.
Now that
Complicated.
we know the switching states of the converter, let's talk about the choice of the device. How do we choose
So how
this
can you
device?
choose
What are the
device for
characteristics
AC
of this
switch?
device? Suppose at any time we know that in any group only one device will be conducting. Let me assume that this device SBA is conducting, right? Now when SBA is conducting, it means that this
So we
potential
can
B
have current
reaches
flow this
over
way.
this point, right? Over the load point.
From
Fine,
input to
over
output.
the phase A of the load, which means that the voltage across SAA is equal to VA minus VB,
So
right?
the voltage
Which is
across here,
VAB, the
VA
line
minus
voltage
VB.
VAB. Similarly, you can see that every switch, whenever the other switch is conducting, the one that is blocking the voltage will be blocking some line voltage. Each switch is rated to the line voltage, and the line voltage can be positive because it's AC, right? It can be positive
So
or
the
it can
voltage
be
could be
negative.
positive,
Therefore,
but also
while choosing
could
the
be
device
negative.
SAA and also all the other
So the
devices,
device
you
should
have
be
to
AC
choose a device
switch.
that has both positive voltage blocking
It could be
as well
positive,
as negative
it could
voltage
be negative.
Let's talk about the currents to be carried by the device. Suppose this SBA is conducting, and when it is conducting, what will it carry? It will
this
carry a
one
load current. Let's
can go this way,
small a, right? Now this load current that SBA is carrying, which is the load current in AC current, of course, because it's an AC.
This is AC current.
It can be positive or it can be negative.
So it could be
So currents to be carried by the devices are also positive as well as negative. Therefore, you need a device
so the voltage
that is
could be
bidirectional
positive,
voltage
could be negative.
and
Current
bidirectional
could be
current.
positive, could be negative. So we need an AC switch, not DC
The
switch.
bidirectional cell.
So bidirectional switch. So it should be
Very
bidirectional.
commonly used topology is two IGBTs with antiparallel
So how
diodes
can
in
we
a common
obtain
emitter
AC
configuration.
switch? So we
This
can
is
use
commercially available
IGBT
IGBT with antiparallel diode and another
DC
IGBT
switch.
with antiparallel diode such that they
So
are
this is
connected
one AC
with
switch.
common emitter configuration. It is possible to have other implementations of the bidirectional switch
So
such
we
as
call
the
this
common collector
AC
configuration,
switch
such
or bidirectional
as
switch.
4 diodes in one IGBT, such as two anti-parallelly
So this is
connected
one
reverse
switch,
blocking
one AC
IGBTs,
switch.
so on and so forth. So what we know is that for now is that the device can carry currents in two directions.
So current can
one
go this
direction
way
and
or can go this
reverse
way.
direction.
So
Right?
AC
And we can
current,
block both positive voltages as well
the
as
voltage can go this way or
across.
this way. So
That
AC
is
voltage.
the choice of the device.
So we can
On to the
use
application
this
of
AC
this
switch.
converter. Why should we use this converter? Classically,
So why
it's
do
not
we use this
commonly
converter?
used converter because of certain disadvantages also.
So
in certain
there are some
applications
advantage
or
and
complexities in its
disadvantage.
operation.
So very
What are
complicated.
the advantages? Why would such a converter be used?
Very
Generally,
complicated.
if you want to do AC to AC
AC
conversion,
to AC,
convert AC
but
to DC,
modulation
and
is
then
very
to
complicated.
amplifier, and then you use a DC link
So,
capacitor, and then
In
you
general, we use AC to DC and DC to AC. This is simple.
The advantage of using a matrix converter over the two-stage AC-DC-AC conversion is
So
one,
what is the
that
advantage?
method is inherently bidirectional.
One stage.
This is bidirectional
From
devices,
here
which
to here,
means
only
that
one stage.
energy cannot only flow from this side
And
to
the
this side,
energy
but
can
also
go
flow
from input
this
to
side
output
to the
or output to
source
input.
side. So the load and source
So
are interchangeable.
bidirectional
Energy
power
flow is
flow.
bidirectional. If you're using a motor drive, it is very easily to go for regeneration.
So we can easily go regeneration.
The second advantage of using matrix converter is that they are very compact in size.
Very compact, small size.
The reason
Because
that they are very
we only
compact in
use
size is
9
because
AC
when you
switch.
eliminate the DC
But for this
stage, you
one,
also
we
eliminate
have
the
6 dial.
capacitor,
And
most
six
of these
switch.
capacitors,
Total
passives,
is
like
12.
capacitors and inductors, are
And
not
huge
occupied a lot of
capacitor.
space, or they have
Here,
a large footprint.
no capacitor.
They contribute to a large volume, large size, but when you're eliminating the capacitor in the DC,
No
you
capacitor.
just have a silicon,
No capacitor. But here,
IGBT
huge
or whatever
capacitor.
devices you're using. You only have power electronics. It's a pure power electronic solution.
So pure
These switches
power
that are
electronic solution. So
AC,
the size is very small.
small sized
Small size.
setup
Compared.
as compared to an AC DC AC converter. Not only will it be compact, but it will also be more reliable. There have been
More
some recent
reliable.
studies that have been done to compare the reliability of matrix converter with AC DC AC converters. The reason it is more reliable is because the DC link capacitors used in AC DC AC converters, they are known to have high failure rates or
So,
high probability.
If you use capacitor,
as
the
it is
capacitor
one
has
component
4-year
of the
life.
DC link capacitor,
Every 4 years,
can
the
convert
capacitor
capacitor
fails.
and then
So you have to
DC
replace the huge
This is a matrix
capacitor.
converter because you do not have anything like an
So we
electrolytic
do not have
capacitor.
any capacitor.
Therefore, its reliability is
So
high,
reliability
especially
is
as power
better.
electronics technology, device technology is improving. Matrix converters have more scope in the future because
So
they
in
are
the
more
future,
focused on power
it is
electronics,
very hopeful.
pure power electronics
People
and
will use more.
solutions as compared to AC/DC AC converters, which also have some passive components. The third advantage of using matrix converters is that they offer improved power quality on the source as well as
So
the
we
grid
can
side, on the
improve
load as
power
well as the
quality,
side, which means not
including
only
power
are
factor
the sinusoidal,
and the
but it
harmonics.
is also possible
So the input
to
is
show
pure
source
sinusoidal.
That's the currents you're drawing from the grid. They are also sinusoidal.
Sinusoidal
in nature.
from
Of
here,
course, when you
voltage and the current.
you will also need a small filter at the input over here, which will help you, which will be a very small sized filter,
So
which
small
will help
filter
you
here
in achieving
obtain
sinusoidal grid currents.
sinusoidal voltage and the sinusoidal current. But for this one, we cannot get good sinusoidal current.
That is improved power quality.
So input power
on the
quality is very good.
low side as well as the high side. The
So
fourth
this is
advantage
an
of using,
advantage.
matrix converters is that you have a completely controllable power factor. So even though your load may be something like an induction
So we can have
motor,
unity
you
power
can
factor.
from the system, but somehow you can control the switches in such a manner
We
that
can control the switch
grid does not
to
see that
obtain
reactive
unity
power
power
is
factor.
controlled. So it will you can
But for
unity power factor,
AC/DC,
but
AC,
even
the
using
power factor is very
which is
poor.
drawing leading wires from the system and compensating for other lags in this lagging loads in the system. So the power factor of the current
So
stream
power factor is good.
unity, it can be leading, it can be
Unity.
it is basically completely controllable in
You can control
fact.
by using the switch.
There are
So
some
this is
other
an
advantages that
advantage.
have been explored recently, that it's a possibility to eliminate common mode voltage, but I think
So we
discussing
also
that
can
in this lecture.
eliminate
And also we
the
can
common
stick to the basic
voltage.
advantages that are known of this converter. Now, the next thing that I would like to discuss with you is a brief introduction to space vector modulation of matrix converters.
So I think we can start here because
Now, I already
what
discussed
we
with you to
learn
when we do space vector
is
modulation.
here.
First thing
So we can
is
change to the second video.
or just sit down and write all the possible switching states of the converter, which we have already discussed that there are 27
So 27
switching states.
switching states. So now we watch another video about a real product. This is Yakuzawa. They developed a matrix converter. So the type is U1000.
Processes across many industries.
So this is real
The
product.
nature of these power converting devices results in distortion, also known as harmonics. To the
So next. Okay. So this is a real product. You can buy it.
Other equipment that share the same power source. Additionally, some variable speed applications have energy that could be delivered back to the power source.
So now we want to do regeneration.
Placed in
We
the form of heat.
get the power from load.
Gully Electric is
The
excited to
source
introduce
we call
a new revolutionary
regeneration
to
energy.
both harmonic distortion and regenerative
And we
energy.
hope low harmonic distortion. So this is Yakuzawa
A new
U1000.
revolutionary variable speed drive to address harmonic distortion and
So
regenerative
reduce
energy.
input harmonic distortion and achieve regeneration energy.
When using conventional
So
drives,
if you use AC, DC, AC, the current is like this. A lot of harmonics. Then it influences everywhere. Then the power quality becomes worse because the current is not good.
equipment in surrounding buildings can be negatively affected.
So this is real
The
current.
problem of harmonic distortion and regenerative energy has required the addition of extra components, such as PWM converters, AC chokes, harmonics filters, and capacitors.
So you need sinusoidal current.
Large space is required to install these external components.
So if we do
Yaskawa
power
Electric
factor
provides the
conversion,
solution.
then we need extra space, extra money to design the power factor circuit.
In a single compact
But now we use matrix converter. We do not need any power factor conversion circuit. We can create sine wave current. So 70% less wiring, 70% less footprint. So it is like this. Very clean, very simple, and very clean. So space reduced 50%.
Thus, total cost of ownership is reduced by minimizing physical space. With
So
the
we need
Yaskawa
space.
converter,
Small space, and only one single conversion.
Motors normally consume energy, but sometimes energy flows backwards when a
So
motor shaft is
sometimes
turned
motor
in an external place.
can return the energy to the grid.
A lifting
Like
application such as a crane
When we
consumes
up,
energy when the
we
motor
draw,
is
we
lifted
need
up.
energy. When we down, we can provide energy
Generates
to
when
the
load
grid.
is lower.
We call it is regeneration.
Dynamometer. In this case, energy is being delivered through a motor back to a variable
So
speed drum
back
so
to
that
the
power can be measured.
grid.
Traditionally, regenerated energy is wasted as heat in a braking resistor.
So in general, we just waste as heat, but it is not good. We have to save energy. So we want to return to
By
grid,
delivering energy back to the power source.
back to the power source.
The Yaskawa Matrix Converter U1000
So
can
now
save
we
up to
develop
50% of
matrix
previously wasted
converter
energy by transferring
to
energy to
return
other
energy
equipment.
to the grid.
Thus, the Yaskawa Matrix Converter U1000 realizes energy saving
Energy saving,
utilizing regenerative energy
effectively
in a single
utilizing
component.
regeneration energy.
Office air conditioning, pumps, refrigeration compressors, escalators,
So escalator,
elevators, cranes,
winds,
engine test systems,
engine
and similar.
system.
The problems these applications used to have can be solved all by this single compact component.
Simple contact component.
Yaskawa's new Matrix Converter U1000
So it is new matrix converter
for all your low harmonic
for energy saving, for regeneration, for low harmonic current. Okay, so we learn from two videos. The first one, we
Welcome to
learn
the Yaskawa Matrix
the
Drive.
basic principle. The second one, we learn the real application for matrix converter. So some company already use this idea to develop a new product. We call it is matrix converter. Okay, so now we will continue to discuss. Okay. So because this part is very difficult, so later I will use the blackboard to explain. So this is the matrix converter. Matrix converter, we call this is input source. This is output sink. So this is current sink. This is voltage. And this is AC switch. If we turn on A and B together, then short circuit. If the whole switch turn off, then we cannot provide the output current. So the rule is for each output line, if and only if one switch is turned off. If more than one switch, then short circuit. Short circuit. If one switch turn off, then you cannot provide this current shift. So the rule is if and only if each output line, one switch is turned on. So we call output is current shift, input is voltage source. So how can we express voltage source? We use this symbol, voltage source. How can we express current shift? In general, we use this symbol. This is current shift. So we have voltage source, we have current shift. So how can we determine which one should turn on, which one should turn off? It is very challenging. So here, our idea is, can we convert the output current shift into output voltage shift? So if you need an output voltage, what do you need? You need a pure sinusoidal output voltage. Then you need a capacitor here to do the filtering to get the pure sinusoidal output. However, if you put a capacitor here, then what happens? So first, the capacitor is 100 volt. Then you switch to the second voltage, it becomes 50 volt. So in 1 microsecond, you change 50 volt, then you create 50,000 ampere charge the capacitor. So the capacitor current becomes infinity. So when you switch, the capacitor current is infinity, then you damage the capacitor. So you can see this circuit is not feasible. Every time you damage your own capacitor. So it is not a good idea. So what can we do? We have to remove the capacitor. We have to put an inductor here to make it become a current sink. So this is the reason we always say the output should be current sink, but not voltage sink. So we can use this figure to explain. But why do we use input voltage source, not input current source? Because in the real world, what is our input from socket? What is the Thai Power Company provide? They provide 110 volt or 220 volt. So they only provide constant voltage. They cannot provide constant current. So can you buy a circuit? They always provide 1 ampere. You cannot get this kind of facility. So we say the input always voltage source, the output always current sink. So we have the basic idea for the structure. We call it is the matrix converter. It is nature. So now we will go into the switching function. So what is switching function? So this is a formal term. You can key switching function, then you can get some data. So now I will use the blackboard to explain what is switching function, because it is very complicated. So now we will move to the switching function of the matrix converter. So we want to discuss about switching function. So we have 3 by 3. So we have current sink. This is current sink. And we have voltage source. So we have voltage source. So we have voltage source, which is constant. So we have input voltage source. And we have output current sink. So we have I1, I2, I3. So this is output. Output is called J. So J is 1, 2, 3, I1. So J is 1, J is 2, J is 3. And the input we call I from 1 to 3. V1, V2, V3. So this is input. So what is switching function? So we have 9 switch. We have 9 switch, 3 by 3. So 9 switch. So we should give the name. Give each switch a name.
So this is H11, this is H21, this is H31, this is H12, H22, H32, this is H13, H23, this is H33. So we have
9 switch. 9 switch.
so how can we call the switch Hij? So I means input. I could be 1, 2, or 3. J means output. Could be 1, 2, or 3.
So how many states can we have for each switch?
So this is AC switch. We call this AC switch. So how many states? If the AC switch could be 1. Here could be 1.
What is 1?
1 means on. If turn on,
Then the H1 line is 1.
if it is turned off, then it is 0.
0.
So this means
Off. So what is 1?
when the switch is turned on. So if you close the switch, then you say the Hij is 1.
If you
Open the switch, then you say
the Hij is 0.
so. If you learn inductor, how can you describe the inductor? You can say it is LS, right? LS. So you know how to model an inductor. If you have a capacitor, how can you say the behavior of the capacitor? Integration. So you can get it is equal to CS. So each device, we can use math to describe it. If you have a transistor, how can you describe the transistor? Then you have input resistance, and then you have IB. Then you have IC, it is beta IB. So we call this is small singular, right? For the transistor. How can you express a transformer? If you have a transformer, then you have input resistance, input leakage inductance, you have mutual inductance, you have output leakage. So this is L1, this is R1. So this is L2, this is R2. Then you have output. So we call this is the transformer mathematical model, right? So each device, we learn a model. So now my question is, if you have a switch, what is the model? Anybody can tell me what is the model of switch? So what is the mathematical model? Of a switch?
It may be high resistance or low.
Pardon me?
What about high resistance and low resistance?
Load?
High resistance, low resistance.
High resistance,
Just like open.
Okay, so-
high resistance.
equal to
Infinite.
1 mega,
Yes.
and the load resistance are equal to 1. So do you use this when you learn electrical circuit? When you learn power system, how can you describe a switch? We never use this, right? So how can you describe
A switch. You think it is simple, But what is the mathematical model of a switch? You are expert, so can you show me what is the mathematical model of a switch? You say it is simple, everybody know it, but how can you describe it? You know transformer, you know transistor, you know capacitor, you know inductance, and also you know generator, right? But how can you describe a simple switch? Then you say, I don't know. Because I have never learned it, right? We don't know. So what is a switch? If a switch turn on, we have 1. If a switch turn off, we have 0. So only 1 and a 0. Only 2 steps. Can you say the switch is 0.5? A switch is 0.5. What does this mean? Impossible, right? Only 1 and a 0. So sometimes switch on, sometimes switch off. But for power electronics, the switch is regular, repeatedly, right? So if you have PWM, then it is like this. So every 1 period, you turn on for fixed time. So we call this is duty, right? So it is repeating. So we can say this is like this. So it is repeating. So 1 0 1 0. So why it is repeating? Because power electronics. Okay. So we call this is time interval from here to here. 1 period. You can say this is 1 period. But I also can say this is 2 pi. Because in general, if you convert into Fourier series, 1 period is equal to 2 pi, right? So then how about this? This is turn on period. This is turn off period. So if switch is on, 1. If switch is off, 0. So this is the switch. So we can describe the switch by using this kind of symbol. So what is this? This is switching function. So we call this is switching function. So what is switching function? If you turn on, then become 1. If you turn off, then become 0. So if I want to describe this, then I can say H11 plus H21 plus H31 have to equal to 1. So this is switching function. If it is equal to 2, then 2 switch turn on. Then what happens? Short circuit. If this is 0, then 9 switch turn on. Then this one open circuit. So according to our rule, if and only if 1 switch is turned on, then how can you use a math to describe it? You can write down this one. Then everybody understand. So if and only if 1 switch is turned on. Then how about this one? This one you can say H12, H22, H32 equal to 1. So very easy, right? How about this one? H13, H23, H33 equal to 1. So now we can use switching function to describe a sentence. And it is very clear and very simple. And we also can use the waveform to describe the switching function. So how can we describe this behavior? So now we want to describe this behavior if and only if 1 switch is turned on,
in each output line. So how can we describe this? We can say this is summation ij equal to 1. And the I is from 1 to 3. And the j could be 1, could be 2, could be 3. So if j is 1, if j is 1, then this is 1. So we can h11, h21, h31 equal to 1. This is j equal to 1. How about j equal to 2? We can say j equal to 2, 1, 2, h22, h32 equal to 1. So we can write down this one, right? If j equal to 3, we can say h13, h23, h33 equal to 1. So this means j equal to 3. But to simplify this equation, we can write down this math. So very simple. Only one equation, right? So summation hij equal to 1. I can be from 1 to 3. So this is the equation. So how about Vj? How about output voltage? So now we want to describe this one. This is output voltage. So this is V1, J equal to 1. This is V2, J equal to 2. This is V3, J equal to 3. So how about V1? If J equal to 1, so we want to check output V1. So how about this voltage? How can you describe this voltage? So if this one turn on, this one turn on, then it is equal to V1 multiplied by H11. So we can say it is equal to H11 V1. If this turn off, this turn on, then V2 come here. It is equal to H21 V2. Right? So we can say H21 V2. If this turn on, these two turn off, then H31 V3. So H31 V3. So this is J equal to what? J equal to what?
Can you just repeat it?
Pardon me?
This equation, can you just repeat?
Repeat this one. Okay. If this one turn on, then this is equal to 1. Right? Then how about this voltage? It is equal to this duty multiplied by V1. If this is 0, this is 1, then it is equal to this duty multiplied by V2. If this 0 is 0, it should be H31 multiplied by this duty. Is it possible this one turn on and this one turn on? Impossible. Short circuit. So you don't need to worry over there. They never over there. Right? If they over there, then short circuit. If they become 0, then open circuit. So we can write down this equation. Okay? So if J equal to 2, we consider this line, this voltage, then it is equal to H12 V1 plus H22 V2 plus H32 V3, the same principle. So we can write down the output voltage is H12 V1, H22 V2, H32 V3. So this is J equal to 2. How about J equal to 3? Then V3 is equal to H13 V1, H23 V2, H33 V3. So we can use switching function to describe the output voltage. So we call this is output voltage. So output voltage is related to input voltage and also related to switching function. Related to switch and input voltage. So if you want to write down these three equations become one equation, how can you say this? So you can say we have Vj, but J could be 1, 2, or 3. So what is Vj? Vj is summation. This is H, Kj, Vk. So Vk is input. So Vk is input. And Vj is output. So this is input. So input could be 1 or 2 or 3. So K would be 1, 2, 3. Right? And then we can say Vj is equal to Hkj Vk. So first we can say if J equal to 1 here, then it is H11 V1 plus H21 V2 plus H31 V3 here, right? If J equal to 2, then here J equal to 2. V2 equal to H12 V1, H22 V2, H32 V3, right? If J equal to 3, V3 equal to H13 V1, H23 V2, H33 V3, so like this, right? So then, originally we have 3 equations, but we think 3 equations is too much. We only like 1 equation, so we can say this way. So 1 equation for output voltage, 1 equation for if and only if one switch is turned on. Okay. So how about input current? So we want to use the switching function to describe input current. So what is input current here? So we have input current here. So we call this is I1. So what is this current? So we can use another symbol because we want to show difference. This is I1. So input we use small I, I1. So what is this current? If this turn on, then the current go this way. So it is H11 I1, right? So if H11 turn on, then what is the current? So we want to write down the current. So the current is II. It is input current. Input current. So first I equal to 1. So this line I equal to 1. So what is the input current? It is equal to H1 I1 plus H12 I2 plus H13 I3. So this current, if this switch on, then it is H11, I1. If this turn on, then it is H12, I2, right? If this turn off, this turn on, it is H13, I3. So we can write down this way. So we can say II is equal to this. And then how about I equal to 2? So I2, I equal to 2. So if I2 equal to H11, sorry, this is H21, I1, H22, I2, H23, I3. So this way. How about the third input, I equal to 3, I3 equal to H31, I1, H32, I2, H33, I3. If I want to use an equation, not three equations, then how can I express the three equation into one equation? So we can say HI is summation HIK, IK. So this is input, this is output. So this is output current sink. So we have here the K equal to 1, 2, or 3. So input could be 1, 2, or 3. So this is input current. So now totally how many equations do we have? We have 3 equations. This is the rule. If and only if one switch turn on. This is output voltage. The output voltage is not independent. It is dependent on switch and the input voltage. Okay. How about this one? This is input current. The input current is not independent. It is not always constant. It is depends on the switch and the output current. Okay. So we have totally we have how many equations? 3 equations. One is rule. Another is output voltage. Another is input current. So we can describe the whole behavior of the matrix converter. So it is beautiful. So if you develop this, you can get a PhD because you use 3 equations to describe very complicated behavior, right? So this is the beauty of switching function. So you can simplify the problem and you can generate very clear conclusion. So we can have 20 minutes break